Hi students, and welcome to another HSC Chemistry video in the acidic environment series. In this one we're just going to quickly review our understanding of reversible reactions and then we'll lead into the application of Le Chatelier's principle. So the first and most important thing to say about these types of reactions is that reversible reactions are ones that do not proceed to completion. If we put some magnesium into a Bunsen burner flame, that magnesium will eventually catch a light and will burn with a very bright glowing flame, and eventually we'll be left with the white magnesium oxide powder. In this case, it's not a reversible reaction because the reaction proceeds to completion. All of the magnesium is used up, provided there's sufficient oxygen, and we don't have any of the products and reactants existing at the same time. We have all reactants, or then we have products at the end. But not all reactions are like this. Not all reactions proceed to completion. Sometimes, once we start with our reactants and produce the products, as the concentration of the product starts to increase, they may themselves interact with one another and start to reform the original reactants. That is, the reaction may actually go both ways. At some point, there will be a stabilization between these two. But wherever we have a situation where, if we talk about the reactants and the products, and so initially we will have all reactants and no products. As the reactants drop and the products climb, if at some point the products start to reform the reactants, then we have what's called a reversible reaction. Now, the important thing about reversible reactions or equilibrium reactions is that both reactions can be occurring at the same time, but they may not be occurring at the same rate. Certainly, initially, if we only have reactant molecules, we will only have reactants reacting, and therefore we'll only be going in the forward direction initially. But once the concentration of the product starts to rise, that's when we will be able to see the reverse reaction starting. So the rate of the forward reaction will slow, the rate of the reverse reaction will increase until we reach a point where they are the same, when the rate of the forward reaction equals the rate of the reverse reaction. And this is when the system has reached equilibrium. So equilibrium is not about equal concentration. Okay, it is about equal rate of reaction. Now, in most situations, we can't see in all situations, we can't see what's happening at the molecular level, but we can sometimes see what's happening at a macro level. If we see color change, if we see gas evolution, if we feel changes in temperature, there'll be a point where these macro changes cease. So there doesn't seem to be any more change that's occurring, and yet what that is telling us is that for a reversible reaction, that the reaction has reached equilibrium. The rate of formation of the products is equal to the rate of formation of the reactants. Now, there's a number of different factors that can affect an equilibrium, and this is often determined by the state in which the products and reactants exist. The other thing that's very important about equilibrium is there are a couple of natural systems that are very important in terms of establishing an equilibrium. We will look at things like blood systems and also some important buffer solutions that we can actually either find existing in nature or actually create ourselves in order to try and maintain a consistency of pH levels. So this whole idea of equilibrium is very, very important in natural systems. But there are a number of different factors that can actually affect the position of equilibrium, so where it lies in terms of equal products, reactants, more products than reactants, or less products than reactants, and how that system can be changed. And there are a number of important factors that we need to consider. Reactions can either be exothermic or endothermic, and obviously if the forward reaction is exothermic, then that means that the reverse reaction will be endothermic, and therefore temperature will affect the position of the equilibrium. We'll push it one way or the other. Pressure is important for gases. Okay, solids can't be compressed, so pressure doesn't have any impact on solids or liquids. And liquids can be not really compressed, I suppose, under super pressure they may be. But pressure is irrelevant for gases because gases can be compressed, and therefore that can change their equilibrium positions. And so can the concentration of either the products or the reactants. If we introduce additional product or reactant molecules, then we can have a shift in the equilibrium. One important note at this point, and we'll have a look at some examples of this as we go further on, but one of the things that can affect the rate of the reaction but not the position of equilibrium is a catalyst. Now we know that catalysts are chemical substances which lower the activation energy. So you remember, this is the energy of activation, and the catalyst, what the catalyst does is the catalyst comes in and it lowers that activation energy. That's a little bit of a hard color to see, so let's go over it with the green. There it is. So it lowers the activation energy. So this here is the new energy of activation, and therefore the reaction is going to occur much more easily, and this is with the catalyst. But what the catalyst does not do is the catalyst does not shift the position of equilibrium. So equilibrium will be reached, it will be reached more quickly, but that position will not change with the use of the catalyst. Thanks for watching.